Hi everyone, my name is Wanlin, and I'm from the Advanced Robotics at Queen Mary, University of London. And today I'm going to give a presentation on F-touch sensor for 3-axis forces measurement and geometry observation. And there will be 5 parts in the presentation, and I will go for the background first. So here we can see some popular force sensors and the tactile sensors. So let me just first give a review on force sensors. So force sensors are used to measure the multi-axis force and the moments, and they could be of 3 degrees of freedom or 6 degrees of freedom. And force sensors usually have a deformable structure, and by observing the deformation of the structure, we're able to measure the net force and the torque. So here, the advantage of the force sensors are they have a high precision and a wide measuring range. However, they cannot measure force distribution. And here is an example of a force sensor that is mounted between a robotic arm and an anti-effector. And it is used to measure the multi-axis force and torque at the joints. And then let me give a review on tactile sensors. And tactile sensors are used for object detection and could provide a tactile feedback. So tactile sensors can measure the pressure distribution. However, they cannot accurately measure the force information, and the measurement range is relatively small. Here is an example of a tactile sensor that is mounted on a robotic finger, and it could provide a real-time tactile feedback during the grasping. So for the objectives, so we can have a force sensor at the joint to provide the force information, and tactile sensors mounted at the ends of the to provide the tactile feedback. Or if we have small force sensors, then we can mount the sensors like this, and so we can have the small force sensor to measure the force information at the end. So the application could be at the end of a gripper or an effector. And the current issue is that force sensor cannot measure distribution, and the tactile sensor cannot accurately measure the force information. So we are aiming to provide a solution which is named as a force and the tactile sensors. So it could measure both the force information and the tactile information within the one sensor. So it is like a one sensor to measure 2 modalities. I created this figure, and it summarized the different sensing technologies that have been used in the robotic force and the tactile sensing system. As we can see among all these sensing technologies, there are optical-based methods used in both sensing systems. So we propose our sensing methodology with the use of the optical-based way. So for the optical-based sensors start use cameras, they usually have a camera to observe the deformation of an elastic structure or a material to acquire the force and tactile information. Here are some examples of the force sensor and the tactile sensors with the use of an optical-based way. And so we use the single vision transducer camera for the dual sensing modality acquisition. And in our sensor, we have an elastic structure which is used to measure the force information. And we have an elastomer component that is used for tactile information. And we use the optical technique to acquire both modality. So as for the sensor architecture, let me first show a figure of a human tactile system. As we can see, there are four different receptors, and here for the Merkur cells, it is located at the top layer, and it is used for the pressure and also the texture perception. And it has the spatial acuity of around 0.5, which is quite dense. And we also have another cells called the Ruffini corpuscle, which is located beneath the Merkur cells, and it is used for the tangible force detection. And we can see it has the spatial acuity of 7 millimeter, which is relatively sparse comparing with the Merkur cells. And we also have the sensory nerves that connects to both cells and to obtain the force and the tactile signals. Therefore, based on this human tactile system, we proposed our sensor architecture, which has a elastomer layer at the top, which corresponds to the Merkur cells for the tactile acquisition. And we also have the elastic structure beneath to acquire the force information. And we have a camera which corresponds to the sensory nerves to obtain both signals. We have also done some reproduction on those the sensors. For example, here's a reproduction of the GelSight sensor, and also the digital sensor from the Facebook, as they have also open sourced their sensor. And however, both of them are not good at measuring force information. I mean, they're not kind of measuring the force like what the force torque sensor does. So we proposed our the sensor, and it has the several components, which I will introduce in the next slides. So it overall looks like this, and we refer our sensor from the GelSight sensor. So as described in the sensor architecture, we have an elastomer component at the top, which can observe the geometry of the contact object. And we also have a elastic structure, which consists of 6 springs and also several magnets for connection. And we also have 3 black markers, as shown here, to measure the force information. So the overall inner structure looks like this. And the bottom view, this is the camera view, so we can see both the 3 black markers and also the elastomer component. So it is similar to the human tactile system, where we have like the Ruffini corpuscles and also the Merkur cells. So when there's a contact, the capture looks like this. So we can see both the markers and also the geometry of the object. And we can easily extract the black markers from the background and record its movement. So by observing this movement and also the corresponding area changes, we are able to distinguish different force torque conditions. So, and we have also done a calibration with use of a commercial force torque sensor, which is the ATI Mini 40, and we mount the commercial sensor beneath our sensor, and we apply different force torque conditions upon the our sensor, and we synchronize both data from our sensor and the ATI sensor. And then with the use of the linear regression method, we are able to generate a calibration matrix, which is shown in the left here. And we have also done, and the results looks pretty good, and it shows a pretty small arrows, and comparing with the GelSight sensor. So here's the demo of our sensor, and as you can see, our sensor could distinguish different force conditions. For example, like the shear force, and let me just skip. And if we apply like both shear forces and the normal force, the sensor could detect the three-axis forces during the interaction. And also, if we apply an object upon the sensor, then we can see both the geometry of the object and also the force information, as shown here. So in conclusion, we are building a sensor that could measure 3 degrees of freedom forces, and also it could perceive the contact geometry. So it achieves the real-time concurrent force and tactile sensing. And that's all. Thank you.